2.6 Related rates, example 3. Water runs into a conical tank at a rate of 2 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So we have a conical tank, which means that we have a cone, and it says that it stands point down. So I'm going to draw a cone so that we can visualize what is happening. Now, they've told us that the tank is a height of 10 feet, so from the top to the bottom is 10 feet, and it has a base radius of 5 feet. We are told that the water runs into the conical tank at a rate of 2 cubic feet per minute. So if water is being poured into this conical tank, it's actually filling it up, which is changing the volume. So when they tell us that the water runs in at a rate of 2 cubic feet per minute, they're telling us that the change in the volume with respect to time is 2 cubic feet per minute. Now remember, as the water is filling up the tank, the volume is increasing. If the volume is increasing, then the derivative, or the rate of change, is positive. So now, we're supposed to find how fast the water level is rising. So the water level is going to be this height right here. Now that changes as the water is being poured in, so I'm going to call that variable h. As the water is poured in, we also have the radius changing as well, so I'm going to call that r. Now, we're trying to find how fast the water level is rising. How fast it's changing is talking about a rate. A rate is talking about the derivative. So we are trying to find dH dt at the instant when the water is 6 feet deep. 6 feet deep is the instant when the h, or the height, is 6. So we need a formula that relates the radius, the height, and the volume together. The volume of a cone is 1/3 pi r squared h. So in order to find the rate of change of the height, we need to take the derivative. Now, watch carefully what happens when we take the derivative. We're actually going to run into a little bit of a problem here. To begin with, the derivative on the left side is dv dt. On the right side, this is actually a product between two variable functions, which means that we're going to have to take the derivative using the product rule. So we will have the first 1/3 pi r squared times the derivative of the second, dh dt, plus the second, that's h, times the derivative of the first, which will be 2/3 pi r dr dt. Now, when we go back to the information that we were given and start looking through our equation here, we actually have some information that is missing. Now, the dv dt, we have that. The dh dt is what we're trying to find. The h we have. Now, the r's that are in here, even though I don't have those at the moment, I can come back up here and I can actually figure out at the instant when the height is 6, I could figure out what the radius is. However, the problem is with dr dt. Even if I go in and figure out what the radius is at the instant when the height is 6, I still don't know how fast it's changing. So since I don't have enough information, I'm going to have to scrap this and start again. So let's come over here and write the formula again. 1/3 pi r squared h. And let's approach it a little bit different. Now that we know we have a problem with the dr dt, the rate of change of the radius, what we need to do is we need to come up with a formula that we can substitute the r out of the equation. So let's look back up here. Notice that when we have the water in the conical tank, that the cone itself and the water are going to be proportional cones. Since they're proportional, I can set up the equation that 5 is to 10 as R is to H. Now, setting up a proportion can be done several different ways. This is just the way that I thought to do it on this problem. But at this point, what I can do is I can cross multiply and say that 10R is equal to 5H. So that means R is 1/2 H. So now what I can do is I can take that 1/2 H and I can substitute that into my volume formula. So now we can say the volume is 1/3 pi, and now I'm going to replace the variable R with 1/2 H, don't forget to square it, and then times H. Now let's clean this up before we take the derivative. So V equals, when we square 1/2 H, make sure both of those get squared. 1/2 squared is 1/4. 1/4 times the 1/3 right here gives me 1/12. Pi H squared times another H is H cubed. So what we've done is we've actually taken the formula for the volume of our cone and we have substituted the radius out of the formula so that we no longer generate a dr dt. So now let's take the derivative again. The derivative of the volume with respect to time, the rate of change of the volume with respect to time, equals, bring the 3 down in front, that'll reduce with the 12, leaving me with pi over 4 h squared dh dt. Now we can go back up to the given information. We can substitute the 2 in for the rate of change of the volume. We can substitute 6 in for the height, and now we can solve for dh dt. So 2 is equal to, 6 squared is 36, 36 and 4 are going to reduce, that gives me 9 pi times dh dt, and then we can divide. So dh dt is equal to 2 divided by 9 pi. Now, as far as the units, remember that the height, this is talking about the differential of the height is measured in a linear unit of feet. So that is feet, and t is time. Time in this problem is in minutes. So our final answer for the rate of change of the water level at the instant that the height is 6 feet deep is 2/9 pi feet per minute.